All right, so here we're going to check out section 8.7, which is about this new thing called Lhopitals Rule. It's the guy's name who made it famous. What is Lhopitals Rule? We'll get there way later. Okay, so just hold on. It's actually completely off topic, at least it seems at first, right? Because remember, this whole chapter is all about integration techniques or transformation techniques, whatever you want to call them. But it's all about how to integrate things. Okay, so L'Hopital's rule is totally different at first. Okay, but before we get to it, let me talk about why we're talking about it now, I guess, and what's going to inspire this. All right, so let's check this out. This is an example here, right? So, okay, looks hopefully relatively easy, right? You got to evaluate this definite integral, okay? Because it's got bounds. You say, okay, so what's the integral of 1 over x? Then you jump into it. And you say, okay, this is the natural log of x, right? You got bounds of negative of 2 and 3. Plug in the upper bounds. So we're talking about the natural log of the absolute value of 3 minus then plug in the lower bound, right? You got natural log of the absolute value of negative 2. Absolute value of 3 is 3. Absolute value of negative 2 is 2. Right, and you could leave it like that. And heck, if you wanted to, you could even think of this as the natural log of 3/2, right? Since you're dividing logs, you can put into one log where you're subtracting, and there you go. There's your answer. Okay, seems pretty straightforward, right? Totally dead wrong. Right? This does not work at all. Okay, now this is something kind of new that could have done even in Calc 1 per se, or let's realize it was an issue, but it never was a problem before because we didn't know how to handle it. What am I talking about? Why is this a problem? Think about this. 1 over x has a huge problem in terms of its continuity, right? It doesn't exist at 0, which is smack dab in the middle of your bounds, right? So if your bounds were, say, from positive 2 to 3, this would be perfectly fine. And it, in fact, would even have the same answer, okay? But the problem is there's an issue with this thing being continuous. So remember, if you have a discontinuity issue, then your integration is kind of off, especially if you have bounds. Okay, think about, for example, the picture of this, right? So hopefully you remember that 1 over x kind of looks like this. Okay, and think about from negative 2 to 3. Basically, what are you after? Over here is negative 2, and then over here is 3. Okay, so what we're after really is, think about it, is this area here and this area here. Okay, but think about that. There's an asymptote, which means the graph is shooting up, following here, right? So how much stuff is actually here? Because remember, it never actually hits the axis here. Since it never actually hits the y-axis here, then you can't, think of it as like a necessarily a finite area. Okay, it turns out, we'll get there later, not with this one, but it is potentially possible for the graph to get so close so fast. You're going to get tired of hearing me saying this word in this video, the word fast, right? But we'll get there. But if the graph were to approach the asymptotes fast enough, then that space is getting smaller fast enough that it is virtually a finite, and not virtually, but it really would be a finite area. But seemingly, this would definitely be infinitely large because it's going up forever. Same thing down here. This seems like it is infinitely large. As a matter of fact, this one is infinitely large, right? But we don't know that yet. That's not the point. The point is that there's a huge discontinuity issue. Okay, so if there's a huge discontinuity issue in your bounds here, then you can't actually do this, integration like this. Okay, so how do I handle this? Normally, when you integrate something with bounds like this, you integrate it, you plug in, or you find out what's happening with this function at the upper bound, and then you plug in the lower bound and find out what's happening at. Hopefully you're seeing my stressing of the word at, right? Plugging in what's happening at 3, what's happening at negative 2. But I can't do that when there's a huge asymptote in the middle there. Okay, think of it, maybe instead of going from negative 2 to 3, what if I went from 0 to 3? Now 3 is not an issue. You could definitely do that, but I can't plug in 0, right? That's the issue. But it kind of what I was talking about a minute ago. You want to talk about it getting closer to, right? So it's all about the rate at which it's getting closer there, or approaching, or hopefully that's talking about limits, right? Which is basically, we got to go back and do some stuff with limits now, in order to, one, because it's just a good topic in and of itself, but also to preface this idea of what's called, these are what's the next section is all about, improper integrals. So improper integrals have some sort of infinite feel to it, right? Sometimes the bounds themselves could be infinity, or there could be an infinite discontinuity, vertical asymptote, somewhere in the middle of your bounds. And we have to now, we can't plug in at because it doesn't exist at, but we can approach it. So we need to handle this idea of limits. So we got to go back and be able to basically recap limits. And so, we're going to recap the, finding limits here, but basically, what is the point of this section? Lhopitals rule is actually for helping to find limits. Okay. Now, the reason why we didn't talk about it back in Calc 1 is because it does require some knowledge or some techniques that we didn't know yet in Calc 1. If you go back, well, I'll talk about that as we get through it. Okay. But quickly, let's talk about these. Well, let's just check this out. So basically, what I want to do is crash course. Hopefully, you remember some of this reviewing, finding limits. There's a bunch of different ways that we talked about back in Calc 1, right? So you can do it numerically, graphically, or most likely the way that most people get used to now is the analytically, right? So numerically, remember those like plugging in numbers that are approaching, graphically, looking at the graph, and then analytically, this is the most useful one. Right, well, let's just do it. It'll probably easier to make sense. I'm going to focus on the analytic one. I mean, the numeric and the graphically is kind of like if you got nothing else, you can fall back on it, right? But let me at least just talk about it. So, like, for example, if I wanted to find the limit as x goes to -4 of this function, okay? To find it numerically, you could, you remember, first off, what this notation is saying is if there's a little minus here, like we'll do some of these later. Remember, there's a little minus there in the power, then you're talking about on the left side. If there's a little plus, it's on the right side. If there's no little minus or plus, then you're talking about, both sides together, or basically the left and right have to do the same thing, going to the same thing. Okay, then the limit would exist and be the same. Okay, so numerically, things like, okay, if you're approaching -4, you could talk about plugging in numbers like -3.9, -3.99, -3.999, and then do the other side, -4.1, -4.01, -4.001, and see what the chart is talking about, right? That's what I mean by numerically. Okay, or graphically, you could just look at the graph and what the heck the graph's doing there, right? Okay, but like I said, I want to focus on the analytic way. So remember the analytic way, and this is the way most people, when they see limits, remember one thing you could do is just plug it in, see what's happening at, right? Again, by plugging in, you're not finding a limit, but you're kind of circumventing it. If you know there's no holes, if you know there's no jumps, then you know that what's happening around it is the same as that, and then you've in essence found the limit. So what I'm saying is you could just plug in -4, right? So if I plug in -4, right? So -4 squared, this would be 16. And then if you plug in -4, this would be +8. And then the bottom, -4 squared, again, would be 16 minus 4 minus 6. Right, so you just add this up. So 16 plus 8 would be 22. And then the bottom, you got, I mean, I don't know. Personally, I would do 16 minus 10, which would be 6. And then you could simplify that, right, and cancel off a 2. So it's like 11/3. It is what it is. Now, again, remember, by actually physically plugging in -4, have you actually found the limit? No. But knowing that there's no holes or jumps, right? Plugging in -4 did not cause 0 in the bottom, right? So if it didn't cause 0 in the bottom, you don't have any, issues there, right? So there's no removable continuity, discontinuity, or non-removable. Hopefully all this ringing a bell from Calc 1. Or again, what you could do is, if you actually typed in the function here, right? So x squared minus 2x divided by x squared plus x minus 6. Okay. So again, if you just went to the chart here, like if you go to the table, right? Again, you could do it numerically, like just hopefully refreshing some memories here. Things like -3.9, right? Or -3.99. Why am I not getting the same thing? Hold on. Oh my God. 16 plus 8 is not 22. 16 plus 8 would usually be 24. Duh. 24 divided by 6 would then be 4, right? And this is why it might be good to actually do two different methods here, because then you can check, right? Because, okay, so what was I talking about? So go back to here, -3.9. See, look, it's 4 something, which, wouldn't be 11/3, right? But anyway, so -3.99, -3.999, right? But you can see the numbers are getting closer to 4, okay? And the same thing on the other side. If I did -4.1 or -4.01 or -4.001, again, they're getting closer to 4. Or you can look at the graph and see it, okay? But again, since there's no holes, there's no jumps, what's happening at would be the same what's happening around it, so this indeed would be the limit, right? Okay, but notice I didn't put an equals, I did that later, right? So by plugging it in, realizing there is no issues, then that would be the same as the limit, okay? All right, so let's try the same thing with 2 now. So if I plug 2 in, 2 squared would be 4. 2 times 2 would be 4, but this would be a minus. On the bottom, 2 squared is 4, plus 2 minus 6. So now the 4 minus 4 is 0, and on the top you have 6 minus 6, which is 0. Okay, so now if you remember, whenever you see 0 on the bottom like this, whoops, you got a problem, right? So what is that saying is this function doesn't exist at 2. You have a discontinuity. Now, if you also get 0 on the top, if you remember, that is a removable discontinuity, right? So if this is a removable discontinuity, what that's saying is there's probably something I could do to remove the problem, right? So back in Calc 1 or whatever, what would you do here? You would then, okay, I can look at the limit here still, but it's all about factoring, right? So you can factor out the x, and it'll leave you with an x minus 2. And then the bottom, all right, you could factor this is x, and then to get to 6, we need 2 and 3. But add to 1, so this would be positive, this would be minus. And you can definitely see now, when x is going to 2, 2 minus 2, this is the thing that's causing the 0 on both the top and the bottom. Now you can cancel it off. But now, after I remove that, I've created a new function that behaves exactly like this one, except for a 2. Because now I can plug in 2, this would be 2 over 5, basically. Right? Again, hopefully none of this is new, right? Same thing here, right? But this one's on the left, right, and then we'll talk about overall, okay? But again, it's kind of the same thing. Plugging in -3 here, -3 squared would be 9, and then plugging in -3 would be plus 6. In the bottom, -3 squared would be 9, minus 3, minus 6. So now the top would be 15, and the bottom you'd have 6 minus 6 is 0. And I probably should stress this, because remember, when you see 0 on the bottom, all that matters is right now is 0 on the bottom. You got an issue, right? The function doesn't exist, so we can't just just whatever's happening at is not going to be about the limit, right? Because here, what's happening at -4, it's actually at a height of 4. There's no hole, there's no jump, so around it is also the same. Limit's the same. Here, what's happening at 2? Nothing. What's happening at -3? Nothing. What's happening around 2 is approaching 2/5 because we can remove the problem. Here, what's happening at -3? Nothing. But notice the top is also not 0, right? So remember, this is what's known as a non-removable discontinuity, right? So if you have a non-removable discontinuity, then you can't, you could factor this, but it's not going to help you, right? Because, nothing's going to cancel. You can't remove it, okay? So that's when you could rely on the graph, or basically, if you remember, hopefully at this stage, if it's removable, it's because most likely it's a hole. If it's non-removable, it's because you have an asymptote, which means the graph is shooting up or down, which you could easily see from the picture, right? Because if it's the same function, and if I look at the graph of this, again, hopefully you realize over here at 2, it's hard to see, but there's actually a hole right there. When x is 2, you could zoom in, and if you get close enough, you'd be able to see it. But at 2, it wants to approach a height of 2/5. Okay, but we want -3. -3, look, there's this giant vertical asymptote happening here. So there's actually nothing happening at -3. But on the left of -3, like if I would approach things on the left side here, look at the graph is shooting up. Okay, so since the graph is shooting up, this would actually be infinitely large. And then, heck, while we're at it here, it's the same one, but now we're on the right side of -3. On the right side of 3, notice it's going down. So then this would be negative infinity. Then the limit overall, if the left and the right are doing something totally different, then this limit does not exist. Okay? So hopefully a quick, well, not this one yet, but hopefully a quick refresher of how to what limits are all about, right? Sometimes you plug the number in and you get an answer out. It's not an issue, so what's happening at is the same as happening around it, so the limit is the same as what's happening at. Done. Sometimes you plug it in, there's nothing happening, but usually the top will tell you what type of issue you have. If it's also 0, remove the problem. If it's not, most likely you have a vertical asymptote. Look at the graph and then see what's going on. Okay. So let's check out 6 here. It's kind of the same thing. You can plug in 0. So if I plug in 0, well, first off, 4 times 0 would be 0. And the bottom, well, let's just write the whole thing. On the bottom, you have 3 times 0, which is definitely 0, right? This is almost pretty obvious that when you plug 0 in, the bottom, whoops, problem. But what about the top? But watch this. E to the 0 is also 1. So really, this is 1 minus 1. So this is 0 over 0. So again, hopefully you're thinking, hey, let's remove the problem, right? So this is a removable discontinuity. Like this one was removable, but how did we remove it? Oh, you factor it and you cancel off the thing that was causing the problem. Here, the x is what's causing the problem, right? Because when x goes to 0, that's the thing that's creating a 0. There's not much you could do with this algebraically to factor it to remove that problem, right? We got an issue there. So I'm thinking it should be removable. I'm thinking this graph has a hole. I'm thinking this limit should exist, but factoring in removing the problem won't work. There's no algebra to do. Okay, this ultimately leads into we need a new technique of finding limits. It turns out to be quite easy, as a matter of fact. And this is one of those things like, man, why didn't they just show me this in Calc 1? But you couldn't, because it turns out you need to know how to differentiate. Okay? So here it is. Here's the actual point. There's this thing called Lhopitals Rule for limits. Okay? I think the hardest part about this is don't abuse it. Don't overuse it, right? It only works in certain situations, but when it does work, man, is it nice. Okay? So what I mean by this is, let's say you wanted to find a limit, right? And when you think of a big fraction here, right? Think of it as you have a top and you have a bottom. I'm not talking about one big function. No, think of it as you're trying to compare the top, its own thing, to the bottom, its own thing, right? So you have two different functions, the top function and the bottom function. Okay? If, when you go to find this, if direct substitution produces one of these, what's known as indeterminate forms, right? 0/0, like we were just talking about, but also infinity over infinity, or any sign version of that, negative, positive, positive, negative, or negative over negative, whatever. But basically 0/0, think of it as nothing over nothing compared to, or I should say, infinity to infinity in some way, shape, or form. If you get one of these, it turns out you can then find this limit by looking at the new limit where you differentiate the top and you differentiate the bottom, which at first is like, wait, what? That doesn't seem like it should work at all. But it does, only because remember what you're realizing, it'll make more sense when we look at examples of why this works. And it's kind of what I was talking about at the beginning here. It's all about the rate at which these things are doing whatever it is they're doing, right? Like see here, when you plugged in the number, you get, like, let's say you get 0/0. That means the top is going to 0. The bottom is going to 0. What's more important than the top is going to 0, or the fact that the bottom is going to 0, but how fast is it going to 0, right? For example, if the top is going to 0 faster than the bottom is going to 0, then this 0 would take over. Right? If the bottom were going at faster, then the bottom would take over. If they're going at the same rate, then they would kind of collide together. Again, that'll make more sense when we look at examples. But the point I'm making is it's all about the rate at which the top is going to its piece, the rate at which the bottom is going to its piece. That's what we're trying to compare. But how do we say rate in calculus? That's what the derivative is. So do realize you are creating a whole brand new limit here. You are creating a brand new collection of functions, right? Because it's the derivative of the top. It's the derivative. Again, don't use quotient rule here. That's not what I'm talking about. I'm talking about comparing the rate of the top to the rate of the bottom, right? So we're talking about how fast is the top doing its thing? How fast is the bottom doing its thing? Or looking at the derivatives. Okay, so let me show you. Let's just do it. So let's go back. Oh yeah, okay. So example 3. I mean, I want to go back and redo number 2. Okay, so it's basically the same function that we just talked about here. So I want to do the limit as x goes to 2 of this x squared minus 2x over x squared plus x minus 6. Okay, so first thing I'm saying, when you direct substitution, right, we did that already, right? Direct substitution produced the 0/0, right? So direct substitution produces 0/0. So first off, what does that mean? Lhopitals rule applies, okay? If you don't get 0/0, Lhopitals rule doesn't apply, okay? So what you could do, instead of factoring this, instead of doing it, you can say to yourself, how fast is the top going to 0? How fast is the bottom going to 0? Right? When we talk about rate, derivative. So you can differentiate the top, which is just 2x minus 2, and then the bottom would be 2x plus 1, right? Now plug in 2. Okay, but if I plug in 2, there's no more issue here, right? Because when I plug in 2, this is just going to be 4 minus 2, and in the bottom, this is going to be 4 plus 1. There's your 2/5. Same answer we got last time when we factored it. Now, is factoring easier than derivative? I don't know. That's up to you, right? But that's crazy how that worked out. Factoring and removing the problem and differentiating the top and differentiating the bottom and looking at the comparison of the derivatives as x goes to 2 turns out to be the same. Crazy. At first, that's like, what? That shouldn't happen, but it does, right? Okay. So the second one, I want to redo 6. Well, actually, we didn't even do 6 yet, right? But what I'm saying here is if I look at 6 now, This is kind of what inspired us to need something new. Again, what does direct substitution? Direct substitution, again, produces 0 over 0, which again is telling you L'Hopital's rule applies. So now we can look at a new collection of functions, or a new comparison, where we look at the rate of the top, which would be 4e to the 4x, right? The derivative of the 4x is itself times the derivative of the inside, which is 4. 1 goes away. On the bottom is 3, right? The derivative of 3x is 3. Now I can just substitute in here. So when I substitute in, this is just going to be 4 times e to the 0 over 3, but that's just 1, and you're left with 4/3. Done. Right? It's crazy because it works out to be so nice and so easy. Well, most of the time. But one thing just to show you, to check, like if you were to graph this, e to the 4x, close parenthesis, minus 1, close for the whole top, and then divide by all of the bottom 3x. Make sure you put that in parentheses as well. Right? I mean, if I look at the chart here, like if we're approaching 0, right? If I did something like, 0.1, 0.01, 0.001, right? 0.00001, right? You can see that it's approaching 1.3333. Basically, the more zeros you have, the more threes you're going to get, right? So it's 1.333 repeating, right? But what is 1.33 repeating? That's the same as 4/3. Crazy. I mean, no, I didn't. You technically got to do the other side as well, but I think the point is made. Okay. So if you get an indeterminate form, it turns out you can take the derivative of the top and derivative of the bottom. Now remember, don't lose the fact that you are completely changing the problem. But what we're doing is, I guess what I'm trying to do is understanding the spirit of L'Hopital's rule. The spirit is, it's not just that this is going to 0 or this is going to 0. It's how fast are they going to 0, right? Taking the derivative of this, taking the derivative of this, then compare the rate at which each one is going to 0. Right? Okay. One couple things with number 3 here. I want to make sure that you don't abuse L'Hopital's rule either. Oh, this is my own notation. When you see me write this, the L apostrophe H, that's just, hey, I've used L'Hopital's rule. That's not a common thing. That's my thing, right? So if you see in notes or whatever, anytime you see that L apostrophe H, I've used L'Hopital's rule. If you want to use that, fine, or write it all out, whatever. It's up to you. Okay, but let me go back to the number 1 here. What I mean by that is it's the same function, but we wanted to do the limit as x goes to -4 of x squared minus 2x over x squared plus x minus 6. Oh, sorry, you can't even see, but whatever. I'm just rewriting that problem, right? But it's the same problem that we did at the very beginning, right? So it's the x squared minus 2x over x squared plus x minus 6. Okay, but remember it was approaching -4. Now, one thing you might do is people abusing, they say, well, heck, let's just use L'Hopital's rule, and you say, okay, so if I take the derivative of the top, you're going to get 2x minus 2, and the derivative of the bottom will be 2x plus 1, right? Now let's plug in -4, right? So this would be -8 minus 2, and then the bottom you get the -8 plus 1, so this would be -10 over -7, right? Which is like 10 over 7. But it's supposed to be 4, right? Remember we did before, you just plugged it in, so this doesn't work, right? I mean, heck, if you think about that, why couldn't I just differentiate it again, right? If this is its own problem, so then you could use L'Hopital's rule again. So if you use L'Hopital's rule again, sometimes that might happen, the top would be 2 and the bottom would be 2, right? The derivative of the top, the derivative of the bottom, so then this would be 1. Whoa. How could you get 3 different answers here? That's not good, right? I mean, the same thing here. You could take the derivative of this one again. The derivative of the bottom would be 0. Now you got problems, right? So what I'm saying is, don't just willy-nilly take the derivative of the top, derivative of the bottom. Make sure that you have an indeterminate form. Right? So make sure if you have 0 over 0 or infinity over infinity, then you can use L'Hopital's rule. Okay? The same thing, what was that? Oh, like number 5. I think the point is made there, but let me at least just talk about it. Remember, it was the same function, x squared minus 2x over x squared plus x minus 6. But when we direct substituted in, we got 15 over 0, right? Or no, it was negative. Sorry. But anyway, you get 15 over 0. So again, my point here is L'Hopital's rule doesn't apply. But just to show you, if you did try to do it, again, this would be 2x minus 2. The bottom is 2x plus 1, right? Technically, you could do it again, whatever, because this doesn't work anyway. But my point is if you did take 0 to the top, 0 to the bottom, then plug in -3, right? You got -8 on the top, and then you got -6 plus 1, which is -5, which is 8/5. Sure, but no way is that going to, sorry, no way is that going to give you does not exist, right? So none of this should have been done anyway. Okay, so hopefully you see that the issue here is if you have one of these forms, Lhopitals rule applies. If you don't have one of those forms, meaning you don't have 0 on the bottom, then you don't have an issue at all. You just plug the number in and you're done. If you get 0 on the bottom and not 0 on the top, the Lhopitals rule doesn't apply, right? You just look at the graph. Okay. But I think what helps with this is not just knowing when to use Lhopitals rule, and not just being able to do it, but kind of the spirit of it. Okay. Well, again, the spirit of it is all about the rate. Like, what I mean by that is like, okay, I think it makes more sense when you go off to infinity, understanding what I'm talking about by this idea of spirit, right? Because, okay, think about if x is going off to infinity. Like, I'm going to look at these three here. If x is going off to infinity, then think about infinity squared. I mean, whatever. But the point here is it's going to be a really big number, right? The top all by itself is going to be an infinitely large number. The bottom, if x is going to infinity, is infinitely large, right? The same idea here, right? If x is going off to infinity, the top's going to infinity. The bottom's going to infinity. Here, the top's going off to infinity. The bottom's going to infinity, right? So what I'm saying is all three of these produce infinity over infinity. Now, usually when you think of, hey, if a number divided by another number is 1, right? I mean, well, I should say a number divided by itself, right? Like 4 divided by 4, 10 divided by 10, or even -3 divided by -3, or even a million divided by a million, right? It doesn't matter the size, but as long as it's a finite number divided by a finite number, you're going to get 1. But when you have infinity, things are weird. But again, it's not. I mean, this one you can almost intrinsically have a feel for it. What I mean by that is just think about it. It's not the fact that this is going to infinity. It's not the fact that this one's going to go to infinity. It's which one is going to go faster, right? What I mean by that is if x is going off to infinity, if I square something as opposed to leaving it alone, this one is going to take over, right? Because it's going a lot faster than the bottom is. Here, the bottom is going to go faster. It's going to take over. Here, they're going at the same rate. Okay, so think of it as like here, the top is going to take over, so the answer is going to be infinity. Here, the bottom is going to take over. So if the bottom is so much bigger than the top, yeah, I know this is weird because the top is infinitely large, but the bottom is infinitely times larger than this infinitely large top, which means that the top is virtually nothing in comparison to the bottom. So, which means the whole thing will be getting smaller, then this would approach 0, right? Here, they're going at the same rate. So if they're going at the same rate, then they kind of collide together. In this particular case, they would collide at 1 because they're the same. Right? Think in my head, I always think of it as when you're talking about things going off to infinity. Think of a number line. I know I'm weird. I was wondering why did they do number lines horizontally? That makes no sense to me, right? I mean, that's just right-handed people dominating the world. I know I'm right-handed too. I shouldn't say it, but think about number lines. Like why is this way positive and this way negative? That doesn't make any sense to me. 0 should be here. Your number lines should be vertical, right? Whatever. That's my own side. But what I'm saying, whenever you think of a fraction, think of it as if the bottom takes over, then you're going to go off to 0, right? And if the top takes over, you're going to go off to infinity. And if they're going at the same rate, then it's going to collide somewhere in the middle, right? Where they're basically going to collide to some finite non-zero number, right? So what I'm talking about here is this is obviously going faster than this one. This one's obviously going faster. Here, they're hopefully obviously going at the same rate. But again, it's infinity over infinity. All of these. You could use L'Hopital's rule. So what I'm saying is, in this case, you could look at the limit as x goes to infinity of 2x over, and now bottom would just be 1. Right? Now, if x is going off to infinity, right, just taking the derivative of the top, derivative of the bottom separately. Now x is going off to infinity, which is going to go up to infinity because it's just 2 times an infinitely large number. Whereas here, if we use L'Hopital's rule, now you're talking about 1 over 2x. And then again, infinite on the bottom, staying put, not going anywhere. 1 divided by something getting bigger and bigger and bigger, it's going to go to 0. And the same thing here, if you did the limit as x goes to infinity, the derivative of the top is 2x, the derivative of the bottom is 2x, which then you can see is exactly the same, would indeed go to 1. right? So, I mean, the spirit of it is the rate at which they're going is really easy to see here, hopefully. But then when you compare the derivative, it's another way of comparing it, right? So it's just crazy how that works out. Okay. All right, so let's check out a couple of these problems here, right? Now, I know. For those of you, if you remember some stuff from Calc 1, you probably could do these problems faster than it would be for me to sit here and write them down, and probably even faster than Lhopitals Rule, but that's okay. Here, let me do this. Well, whatever, let's do one at a time. Well, okay, so here's my point. So if you remember, I mean, this problem we could have totally done from Calc 1, right? So what are we talking about? The limit as x goes to infinity, okay? So the point here is, if you were to direct substitute infinity, and yes, this is 1, but this is a negative infinity here, right? It's a negative number times something really large. So this is going to take over compared to 1. But this is really going to take over. So if x is going on to infinity, all that really matters is this, okay? This is the thing that's going to take over, but that's just going to be infinitely large. Same thing on the bottom. This is the highest power. This one's going to take over. You're going to go to infinity. Okay. Now, what we did in Calc 1 is you say, okay, yes, the top is going to infinity. Yes, the bottom is going to infinity. But the bottom has a larger degree, which basically means it's going to infinity faster. Since it's going faster, then it would take over. And if this takes over, then the limit would then be 0. Done. I'd buy that argument. But the point that we're trying to make here is you could have used L'Hopital's rule, right? I should probably write that so you know. I'm actually using L'Hopital's rule here because you get infinity over infinity. So the top is 2x minus 4, and the derivative of 1 goes away. Then the bottom would be like 18x squared minus 8. 3 goes away. Now, if I plug infinity in, this one's still going to take over, so it's still infinitely large. This one's going to take over, so it's still infinitely large. Again, yes, you can see the bottom is going faster than the top. So again, it's going to be 0. But the point here is L'Hopital's rule still works because it's still infinity over infinity. So technically, this is still indeterminate form, right? Again, hopefully, obviously, this is going faster. It's going to take over. But without putting that much thought to it, just look at it. Infinity over infinity. L'Hopital's rule works. So then the limit as x goes to infinity. Oh, I can take the derivative of the top would be 6. And then the bottom, when you take the derivative of this, the 18 times 2. What is that? 36x, right? And then obviously the 4 and the 8 go away. But now direct substitution. Oh, the top is 6. It's not going anywhere. The bottom is infinity. 6 that's set in stone divided by not going anywhere, divided by something getting larger and larger, will then, even more obvious, hopefully approach 0. But again, the point is it helps to confirm that idea of this is going faster than the top. Why? Because the rates are going faster comparison-wise because of the derivatives, right? All right. So I think, well, I tell you what, let's do this. I think with 2 and 3, I'll let you guys do these, right? Because hopefully, but hopefully you can see the point here. You can do these relatively quickly. Well, okay, let's be honest. Am I going to ask you about 2 or 3? Probably not, because honestly, they're just too easy, right? But hopefully you can at least see the spirit of these, right? What I mean by this is if x is going out to infinity, the top is definitely going to be infinity, and the bottom is definitely going to be infinity, right? So you have that infinite over infinity feel to it. Okay, so you could take the derivative of the top, the derivative of the bottom, check out L'Hopital's rule. But hopefully eventually you'll see they're going at the same rate. So if they're going at the same rate, you're going to get some number. What is that number going to be? That's 6 over 3 or 2. Maybe I should do this one just to show you. Okay, so what I'm saying is with the second one here, x is going out to infinity. This one's going to go to infinity. Infinity over infinity. So L'Hopital's rule applies, right? So if you were to actually use L'Hopital's rule here, derivative of the top would be the 12x plus 8. The derivative of the bottom would be the 6x minus 6. Okay? And now again, direct substitution, right? Every time you use L'Hopital's rule, try direct substitution first. So plug infinity in. This is going to take over as infinity. This is going to take over on the top or the bottom. This is infinity. So it's still infinity over infinity. So you can use L'Hopital's rule again. right? The derivative of the top is 12, and the derivative of the bottom is 6. No more x's. Sure enough, what are you going to get here? This is going to go to 2, right? I mean, 12 divided by 6 is 2. But the point is you could have just seen it. This is what we did in Calc 1, if you remember. If the degrees were the same, you could just divide out the leading coefficients. Because the top and the bottom are going at the same rate. So it's kind of like what I was talking about here. If the top and the bottom are going at the same rate, they're going to collide at some non-zero finite number. In this case, it happens to be 2, right? So then, again, I think you get my point here. 3, you could use Lhopitals rule here. But again, hopefully this one's real obvious-ish, right? The top's going to infinity. Bottom's going to infinity. But what the point is the top is going to take over, right? There's going to be more x's if you keep differentiating than with the bottom, right? There's more x's on the top than the bottom. So that one's going to take over, which means this would indeed go off to infinity, right? Because the degree of the top is larger. But again, hopefully you can see Lhopitals rule, okay, without actually doing it. That's the other thing. Like, I think what's especially moving forward, because remember where this is going to go is we're going to be using some of these techniques in an integration problem, and sometimes that might require several of these. So sometimes you want to be able to use Lhopitals rule without using Lhopitals rule, right? If that makes sense. What I mean by that is understanding the spirit of Lhopitals rule, right? The spirit of Lhopitals rule says the rates, the derivatives are going at the same, they're going to collide, right? The derivative of the bottom is faster, it's going to go to 0. The rate of the top is faster, going to go up to infinity, right? Without actually taking the derivative, right? So that's kind of what I'm talking about with 4. All right, so let's check this one out. All right, so yes, direct substitution. You plug in infinity. E raised to some infinitely large number is still going to be really large, infinity. Same thing on the bottom. You got x squared, this is infinity. Okay, so you got infinity over infinity. Both top and the bottom are infinitely large, so Lhopitals rule does apply, meaning you could do the limit as x goes to infinity. The derivative of the top, which would be the 3e to the 3x, and then all by itself, the derivative of the bottom would be 2x plus 5. Again, direct substitution. This is going to be 3 times e raised to some infinitely large number is still infinitely large. The bottom is 2 times some infinitely large number is still infinitely large. What does that mean? You can do Lhopitals rule again. Okay, so if I take the derivative at the top, right, this is going to be itself again, but then change one more time by another 3, so it's really going to be 9 now, and then the bottom is just 2. Now, the top is going to be infinitely large, and the bottom is only 2. So that means it's going to be infinitely large. Again, the point is when you get used to this, I would buy if you just use your brain and think about this. Again, yes, the top is infinitely large. Yes, the bottom is infinitely large. But which one of these pieces is going to go to infinity faster? This is an exponential. This is incredibly fast. This is a polynomial. Yeah, it's fast, but it's nothing in comparison to an exponential, right? I mean, you don't even have to go out that far. I mean, like, imagine, I don't know, 10. What if I did e raised to the 3 times 10, right? The bottom is already 1.06 times 10 to the 13th, right? This should be moved over 13 decimal places. It's enormous. But the bottom is only roughly 100. Yeah, okay, it's 150, but who cares, right? The bottom is only 100. Look at the top. It's already enormous, right? It's going way faster. That's why it takes over. Lhopitals rule helps to prove that, but in the future, you want to be able to look at this and say, hey, that's going way faster. It's going to go off to infinity, right? All right, same basic idea with 5. We could do the limit as x goes to infinity. 5x cubed minus 6x squared over 2e to the 5x. Again, when you get good at these, you could probably just like, I would buy if you just look at that problem and told me the answer. But that's okay, we'll get there. But here's my point. X is going off to infinity. So the top, this is way, I mean, okay, well, first of all, that's another indeterminate form here, because this is infinity and this is infinity. But what's infinity minus infinity, right? Because technically the top is infinity minus infinity. Usually something minus itself is 0. But again, this one is going faster than this one. So this would actually take over and be infinity. But the bottom is going to be infinity as well, right? Because it's infinitely large. But if you just think about it, okay, which one's going to go faster? This is an exponential. This one should go a lot faster. So if the bottom is going faster, you would think it's going to go to 0 then, right? Because the bottom is going faster. I buy that argument, and which turns out to be 100% true. Okay, but if you need to, you can go through the whole thing because technically you get infinity over infinity. So Lhopitals rule applies. So we can now look at the limit as x goes to infinity of the derivative of the top. It's going to be 15x squared minus 12x. And the bottom, right, multiplied by the derivative inside be 5. So it's really like a 10 e to the 5x. And technically this would be infinity minus infinity on the top, but this one's going faster again, so it's going to be infinity over the bottom infinity. Still indeterminate, so you could technically use Lhopitals rule again. The top is going to be the 30x minus 12 over now a 50 e to the 5x. Now, this is really an infinitely large number minus a finite number, so this is definitely going to be infinity, and the bottom is still going to be infinity, which means the Lhopitals rule would apply again. The derivative of the top would be 30, and then the bottom would be 250 e to the 5x. Sorry, the derivative of the top is just 30, and 12 goes away, and the derivative of the bottom is multiplied by 5, right? So it's another 250 e to the 5x. But now the top is staying put at 30, the bottom is infinitely large, so this would indeed now go to 0. Notice I'm not writing equals, so don't write equals, right? But whatever, it's not a big deal. But again, hopefully you're kind of seeing the point of, especially if you had an exponential, think about that. What is the derivative of an exponential? It's itself over and over again. It doesn't matter how many times you do this, that exponential is never going to go away. Now, a polynomial, like you might be there a while, but imagine this for like x to the 100. You could keep doing it, but then you take the derivative, it'd be x to the 99, then 98, then 97, then 96. So you might have to do L'Hopital's rule a bunch of times, but no matter how high that power is, eventually it's going to go away. That exponential is never going to go away. Hence, the exponential is going to go way faster than any polynomial, even if the power was enormous. Okay, but eventually that exponential is going to take over. Okay, and it would indeed, well, in this case, it's on the bottom, it takes over at 0. In this case, it was on the top, that's why it was infinite. Okay. All right. All right, so let's check out another one here. Let's check out 6. I think as you're doing these, it's not only just about finding an answer, but it's about understanding how L'Hopital's rule works, the spirit of it. I keep talking about that. But it also is kind of being able to rank the different types of polynomials. Like exponential is way faster than a polynomial. Here, we're talking about polynomial, and we're talking about a log. Okay. One thing, whoa, hold on. I might want to step off. We'll come back to this. But quick review. When you see a log, what I think is really going to help, not only this stuff here, but when we get to the next chapter, or actually 2 chapters later, it's really going to come into play. Remember, this is what a log graph looks like, right? Remember, it's the exponential graph, but flipped over the line y equals x. So remember, there's no graph over here, right? You can't take the log of a negative, right? There's a vertical asymptote here. Or think of it as, if x is going off to infinity, yes, this is still shooting up, right? So if x is going to infinity, the natural log of x is still going to infinity, okay? But a natural log is really, really, really slow, right? So what I mean by that is, look, like if I were to do the natural log of 100, the natural log of 100 is less than 5, right? The natural log of, I don't know, some ridiculously large number, it's only 13. Right? So remember, log is the inverse of an exponential. So remember the problem we did a minute ago? Exponentials are ridiculously fast. Logs are ridiculously slow. Okay, so they're opposites of each other, basically. Okay, we'll talk more about it later, but then there's also this issue over here. But right now, I just want to remember this graph here. So if x is going off to infinity, this is going to go to infinity, and the top is going to go to infinity. Okay. Now, again, you could say to yourself, okay, which one's going to take over? Is my polynomial going to take over, or the log going to take over? Until you get good at this, you can actually see that L'Hopital's rule applies and do it. But hopefully, you're seeing my point here with the whole rate of log. A log is going to go really slow, right? So that means the polynomial is actually going to take over, and it would actually go to infinity as opposed to 0, right? Because it's on the bottom. But again, you could use L'Hopital's rule to prove it, right? So you'd have the limit as x goes to infinity. The derivative of the top would be the 8x. And the derivative of the bottom is 1 over x, which helps to see, wait a minute, the derivative of natural log on the bottom is a 1 over x. But that, I'm not using Lhopitals rule here, I'm just using algebra. Dividing by 1 over x, that is the same as multiplying by the reciprocal, 1 over x. So actually, the derivative of a natural log actually puts even more stuff on the top. So it makes the top even more powerful now, because this would just be 8x squared, which would definitely shoot off to infinity. Which again, hopefully you see what I'm saying is this is going to go a lot faster than this one, right? Okay, check out 7. So with this one here, you're talking about the limit as x goes to infinity of the natural log of 3x over 7x. So again, hopefully you're thinking, okay, x is going off to infinity, multiplied by 3 is still a really big number. Natural log of a really, really big number is still a really, really big number. So this is going to go off to infinity. The bottom is going to go off to infinity. But if you're following my larger point here of being able to rank these things, you're probably hopefully thinking already, this is going to go a lot faster than this one. So we're thinking it's probably, hopefully it's going to go to 0, right? Because that polynomial should go faster than this log, which it does, okay? But if you go through the whole thing, you can prove it. So Lhopitals rule, right? You take the derivative of this, which, okay, so a long way, no, sorry, I need the limit of x goes to infinity. The derivative of the top is 1 over the inside, and then technically the derivative of the inside, which is 3. And the bottom, this would be 7, right? The derivative of 7x is just 7. Or really the 3's go away. But look, again, what happens? The derivative of natural log of x puts an x in the denominator, which means it's putting even more stuff in the denominator, right? Because that x is in the denominator. Which means this is kind of like 1 over infinity, which is definitely going to go to 0. Okay. But again, it's hopefully solidifying that idea of that polynomial thing is going to go a lot faster, even though it's only linear. I mean, this is a linear function is going faster than a log, right? I mean, you probably could see it better on a calculator, right? I mean, if I just did plain old, x, if I did plain old x and I did natural log of x, right? So on the graph, there's x, and then there's natural log of x. See how it's way underneath there, right? So even just a simple line is going up faster than a log is. A log is really slow. Okay. All right. What about 8? All right. So that's number 8 here. This should kind of look familiar, maybe. If you remember anything from Calc 1. As a matter of fact, we did this in Calc 1 already, and maybe you even know the answer to this. But we didn't know it then, but you could have used Lhopitals rule even back then. We didn't know how to do it then. But the point here is by direct substitution, x is going to 0. So sine of 0, remember, is 0, and x is going to 0. This would be 0, right? Okay, so now you say, okay, it's going to 0 over 0, so I could use Lhopitals rule. So Lhopitals rule applies. Now you might want to say to yourself, what about the rate of these? Now remember, we're not going off to infinity here, so things get a little weird, right? X is going to 0. So we're talking about the rate at which x is going to 0 and the rate at which sine is going to 0, right? I mean, it's hard to visualize that. So which one is going faster? Is sine going to 0 faster, or is x going to go to 0 faster? This would be great. Pause the video and take an educated guess. What do you think, right? Which one is going to go faster? It turns out they go the exact same rate, which is crazy, but it's true. How do I know that? Well, let's do Lhopitals rule. Okay, so Lhopitals rule says the derivative of the top, right? Only because it's 0 over 0. It's in indeterminate form. The derivative of the top is cosine x, and the derivative of the bottom is 1, right? Now we can direct substitute it in. So this would be cosine of 0, which indeed is 1. So this limit is actually 1, right? Because so basically, since they collided together, that's basically saying that they're going at the same rate, right? All right. Now with 9, everyone says, "Oh, look, it's the same problem, right?" Because we're talking about sine x over x, so this should be 1. No. Make sure you pay attention. The one we just did was x was going to 0. This is x is going to infinity, right? So you say, oh, okay, so let's use Lhopitals rule here. And so the limit is x goes to infinity. This is cosine x over 1. And then what the heck? If x is going off to infinity, what is cosine going to be doing? all kinds of problems here. Wait a minute. Whoa, whoa, whoa. Before you just start using Lhopitals rule willy-nilly, you got to make sure that it even applies. Okay. What I mean by that is, okay, yes, the bottom for sure is going off to infinity. If x is going to infinity, then obviously x is going to infinity. But is sine going to go off to infinity? Right? Is it really? No, it's not. Right? Think about. Remember? Oh, I got it here. Someone else will do it. Um, Remember what sine does? Well, even better. So we're not here on there. Right, I'm just changing my window from -1 to 1. So remember, just sine bounces back and forth between -1, right? So it goes up and then down, and up and then down, right? But it's going to keep doing this forever, up and down and up and down. So I mean, like, let me get rid of this. No, stop. For example, if I were to look at just x, right? If x is getting larger and larger and larger here, what's happening to this function? It's just shooting up. It's just getting larger. It's getting larger and larger and larger and larger. It's I mean, it is technically not approaching a number, so it is technically does not exist, but it does not exist in a very special case because it's just getting larger, right? Whereas if I did something like, I don't know, imagine you had 3x divided by x, right? So if I did 3x divided by x, I know that's 3, but that's my point, right? Because then eventually it's going to be right there at 3. Oh, you can't see it because it's off the grid, but whatever. So I changed the window, right? There it is. So it's right there at a height of 3, okay? Or I think what might even be better, what if I did 3x and divided by x plus 1? But the point there is eventually, if you went way over here at infinity, right, it's a crazy curve to it, but way over here, see how it wants to go to a height of 3, right? It does. The original x is just going up and up and up and up. This one is not doing that. It's flattening, and there's like that imaginary fence, and it's a boundary. It's not allowing it to go past 3, okay? But sine isn't doing any of that, right? It's not approaching a fence. It's not just increasing or decreasing without bound. It's bouncing back and forth, right? Where did it go? Did I turn it on? Oh, I didn't turn it on. Okay. So it's just bouncing back and forth, right? It's going up and down, right? It's not approaching a fence at all. It's not just going anywhere. So technically, this limit doesn't even exist to begin with. So what does that mean? Lhopitals rule does not apply. Okay. So you cannot use Lhopitals rule here. So don't abuse it either. So how do I do this limit? Well, here's the thing. Yes, sine x is definitely bouncing back and forth. So if x is going off to infinity, does that limit exist? No, it does not. But here's the thing. What is sine x bounded by? It's bounded between -1 and 1. Yes, it's changing, but it's never going to go above 1, right? So what does that mean is the most it could ever hope to be, the largest number. I mean, we're talking about x being infinity, right? So the bottom is, 10, a million, 17 billion, whatever, a really, really big number. But what's the biggest the top ever hopes to be? 1. So if we were to compare this to the limit as x goes to infinity of 1 over x, this is obviously going to go to 0, right? Because the top is 1. But this is going to be even worse because this is something even smaller than 1. It never is going to go above 1, right? So this limit is going to be 0 because the top never even passes 1. And if it were 1, this is really 0, right? So the point there is just understanding how those things work and then also realizing L'Hopital's rule does not apply. Okay? All right, let's try 10. So with 10, we got the limit as x goes to infinity, a sine of 1 over x divided by x. Kind of the same thing, but totally different, right? So first you're thinking, oh, L'Hopital's rule is not going to apply. Yeah, but does it? Because think about if x is going to infinity, this 1 by itself, this 1 over infinity is indeed going to go to 0, which means the top would be, as x goes to infinity, this is going to go to 0. So this is going to go to sine of 0, which is indeed 0, right? And then the bottom is going to be infinitely large, right? So, but that's the key is that you have to realize if x is going off to infinity, this is going to go to 0, right? And then sine of 0, right, is basically 0. But the bottom is infinitely large. Okay? I don't know why. Whatever. Uh, Man, this leads into a much better problem I just thought of off the top of my head, right? But we'll check that out in a minute. But because this is boring, right? But I think the reason why I did this problem is don't abuse it, right? So I guess what I'm saying is the top is going to 0 and the bottom is going to infinity. This is not an indeterminate form, right? So what is this going to be? Think of it as, yes, the bottom is huge, but the top is 0. What's 0 divided by a non-zero number? Still 0, right? So this is just going to be 0, right? Yeah, so I mean, yes, the bottom, or even think of it as, normally when you think of a set number divided by infinity, this is going to go to 0. But the top is already 0. So think of it as the top being 0 and the bottom being infinity is going to make it want to go to 0. So it's almost like a double 0, right? The top is already going to 0 and the bottom being infinitely large will make it want to go to 0 as well. So both of them want to make it go to 0, right? Okay. So what I was just thinking, let's do 11. I'm just making this up. And I think maybe this is what I originally meant. I just typoed it because that's almost too easy. What about this? Okay, this is a much better problem, right? Because what is this? If x is going to infinity, right, what are we talking about here? 1 over infinity is going to go to 0, right? So now the top is going to be like sine of 0, which again is 0. But the bottom, if the bottom were a fraction in and of itself, right, x going to infinity, 1 over infinity is now going to go to 0. Oh, now the top is going to 0, but the bottom is going to go to 0, right? Now we have an indeterminate form. Now Lhopitals rule would apply. Okay. So now I want the limit as x goes to infinity. Take the derivative of the top, right? So this would be cosine of 1 over x. But then chain rule is not multiplied by the derivative inside, but maybe think of that as like x to the negative 1. So you take the derivative of that, bring the negative 1 down, then subtract 1 would be like negative 2, or it's like negative 1 over x squared. But look, the derivative of the bottom is the same thing, negative 1 over x squared. Right? I mean, like the inside here, so when I chain rule and take the derivative of it, and then I use Lhopitals rule and take the derivative of the bottom, they're going to be the same thing. So what happens? These are going to cancel. So you're going to be left with the limit as x goes to infinity, cosine of 1 over x. Which now, if x is going off to infinity, again, this is going to go to 0. So this is going to go to cosine of 0, which is 1. So this would actually go to 1. Right? But again, it's bigger pictures, knowing when to use Lhopitals rule and when not to. Okay? I think just for time's sake, there's a lot more to this, right? Because, I mean, honestly, what have we done? There's not a whole lot here, right? Yet. It's just, hey, when you have one of these forms, take the derivative of the top, derivative of the bottom, plug it in, right? It turns out there's a lot of other indeterminate forms that we need to make look like this, okay? But I'm going to save that for another video. So right now, these are just the ones that you can apply in Lhopitals rule 2. And you'll see the rest later.